Good afternoon, everybody. I hope you can hear me. So we are starting with chapter number 27, which is Gauss law. Okay. So chapter number 25 and 26, the PDFs are already shared on the Google Drive. Please use them. Okay, and prepare for the examination. Test one should be around the corner, so start your preparation. Now, coming to what is there in Gauss law, before we start that, let us just quickly see what we have actually studied in chapter number 26. In chapter number 26, the main job was to introduce the concept of an electric field, and then electric field because of a single charge, because of a dipole, because of combination of charges. Basically, we talked about charge distributions and their electric fields. So this is what we have done. And how did we find the electric fields? We have simply used the equation E is equal to F by Q naught. E is equal to F by Q naught, where F is the Coulomb's law. So we just used Coulomb's law, and then we used the principle of superposition. And for a system of discrete charges, if we had a collection of charges, we just applied the principle of superposition to get the net field. And similarly, when we had continuous charge distributions, what we did was we took into account the symmetry. One component of the electric field might cancel out. Okay, like for example, we talked about the line charge and the electric field due to the line charge on the perpendicular bisector at some distance y. So we talked about symmetry and we cancelled out some component of the electric field, and for the other one, we just did an integration. But then you found that it was mathematically very taxing. First thing was you had to deal with vectors which were all, infinite number of vectors which are all in different direction, and then doing their integration and then knowing the formula for this integration. All this was pretty taxing. Okay, but now we are coming to chapter number 28. This is 27. This is chapter number 27. In chapter number 27, on the other hand, what happens is, not chapter number 28, it is chapter number 27. In chapter number 27, what happens is we will see that, okay, we will once more find the electric field due to certain charge configurations, maybe discrete charges or continuous charge distribution, but then we evaluate electric field using Gauss's law. We use Gauss law, and Gauss law is more simple to use, mathematically also simple, and this concept of Gauss law is going to be useful. And the approach that we take using Gauss law is again employable in situations where there is symmetry. You can't use Gauss law everywhere. You have to use Gauss law only in those situations where you're going to see a symmetry. But then it makes your job mathematically quite simple. Okay. Now let's go to the next slide. So here I'm listing out the importance of Gauss law. The first thing is Gauss law is a more fundamental law compared to Coulomb's law. Gauss law is a more fundamental law when compared to Coulomb's law. In the sense, Coulomb's law is just a special case of Gauss law, or Coulomb's law is contained in Gauss law. Gauss law is much more general and more fundamental. That's the first thing. The next thing is Coulomb's law is a special case of Gauss law for point charges, which is actually part of the first point. Next thing is Coulomb's law was applicable only when the charges were at rest or at most moving very, very slowly. But please remember, Gauss law can be applied even to rapidly moving charges. Meaning, Gauss law can be applied even when you don't have electrostatics. Gauss law can be applied. So you can see that Coulomb's law is just a special case of Gauss law. And Gauss law is also one of the four Maxwell's equations. Okay, actually two of the Maxwell's equations are Gauss laws. One is Gauss law for electrostatics and the other will be Gauss law for magnetism. So these two will get into the four Maxwell's equation. So in that sense also Gauss law is more fundamental. Coulomb's law is something that you will study at the beginning of this electromagnetism and then forget it. But then Gauss law is something that you are going to keep on using again and again all through your engineering, especially if you are going to be doing communication, or if you're going to, let us say, if you're doing EC especially, you will require these four Maxwell's equations again and again. And the next thing is, as previously mentioned, Gauss law is a simpler way of calculating the electric field. And here also we take into account the symmetry of the charge distribution and the symmetry of the field. What this means, we will understand as we go along. Any doubts so far? Any doubts? Looks like this section has no doubts at all. How many are in the class? Let me see. Just 42. So nobody has any doubts?
No, ma'am.
So let me first introduce the word flux. We have to now introduce the word flux. How many of you heard this word flux other than in the context of physics? So nobody has heard. Okay. So let me come back to physics. So let's see what is flux. Flux is a measure of flow or penetration of field lines. We have seen in the last chapter field lines. Okay. So it's a measure of the penetration of field lines through an imaginary fixed surface in the field. Let's say we are talking about electric field. These are the electric field lines we are talking about. And if we are able to put a surface here, then three of these lines are cutting through. Field lines are cutting through the surface. Okay, measure of this penetration or flow of electric field lines through some surface is called flux. Doesn't mean anything right now, but then let us just take some example, then maybe you will understand. What we are showing here is, remember when I introduced the word field, I used to talk about something called velocity field. Velocity field. Velocity field is simply mapping the velocity of the fluid at every point in the pipe. So let's first of all talk about parallel and uniformly spaced velocity field lines. What does this physically mean? If the velocity field lines are parallel to each other and uniformly spaced, what does that mean? I'm talking about water flow through a pipe. Okay, through a pipe, water is flowing. And at every point in the pipe, if I am able to measure the velocity and I find that these velocity values are all equal, then this velocity field can be represented by parallel lines which are uniformly spaced. That means this is a steady flow. This means that it is a steady flow. There is no turbulence in the flow. The rate at which water will be entering the tube will be the rate at which the water will be going out also. There is no turbulence anywhere. Cross section is also the same. Okay. Now what we'll do is, let us take that kind of a field, velocity field, and then take a wire and bend it into the form of, bend it so that you are able to get a rectangle. Bend a wire, okay, and then make the two ends meet, and what you get should be a rectangle. This is a rectangular loop, and let A be the area enclosed by this wire. Is this point clear, guys?
Yes, ma'am.
So you're taking a wire and then a straight wire and then bending it and forming a rectangle. Okay. So there is an area enclosed by this rectangle. Let that area be capital A. Okay. So now what you do is, the flow is like this. This is my electric field. Now I will let the boundary of my cell phone represent this area. Let the boundary of my cell phone, this is my cell phone, let the boundary of the cell phone represent my area. And this is my flow. Okay. Now, if I hold the area like this, so that the velocity field lines are all perpendicular to the surface formed by this area. This is the surface formed by the area. And if my velocity field lines are all perpendicular to this area. So this is what is shown in the first picture. Okay, we are not showing the area. If I show the area like this, it will look like a line. Okay, therefore we are just showing a line here. Okay, this is basically an area. So we are holding the area in such a way that the electric field lines everywhere will be perpendicular to the face of this area. Or now what we'll do is we will define, there is a blue arrow you can see there. We will define something called a normal vector. Normal means perpendicular. So perpendicular to this area, we are going to define a vector, a unit vector called n cap. N cap. Okay. And you're going to see here that the velocity is parallel to n cap. I hope you understood what is n cap. N cap is this is my area vector. N cap is a normal that you're drawing. If I draw a unit vector normal to the surface, that is called n cap. And you can straight away see that the velocity vector and n cap are parallel to each other. Now, if I want to find out what is the fluid that has crossed this area, so water is flowing like this, what is the fluid that has crossed this area, flown through this area per second? If I want to find out what is the volume of fluid that has flown through this area per second, all I have to do is just multiply V into A. Just multiply velocity into A. Okay, and what is the unit of velocity? Meter per second. Unit of A is meter square. So what am I getting? Meter cube per second. Meter cube is the unit of volume. Meter cube is a unit of volume. So when I say that the product of V and A gives you meter cube per second, then I am saying that it is just giving how much volume is crossing per second. Meter cube is volume. So what is the volume of fluid that is crossing this area per second? Or volume flowing per second can also be called the volume flow rate. It can also be called the volume flow rate. This volume flow rate is called the velocity flux. This is called velocity flux because we have calculated this for velocity field lines. We have taken our field lines as velocity and then we have done it. Therefore, it is called the velocity flux. And velocity flux is denoted by the symbol phi. It is denoted by the symbol capital phi equal to, okay. So let me say, just now we have seen that phi equal to V into A for picture 1. For picture 1. Okay. Next what we'll do is, we will take the same flow is happening. Only thing is now, we are not going to hold this area. We are not going to hold this area of the loop perpendicular to the flow. We are not going to do that. Instead, what we'll do is, we'll just bend it like this. We'll just bend it like this. When you bend it like this, the amount of water that can flow, the amount of fluid that can flow is now not going to be this entire area. It has got reduced. It has got reduced. Okay? And actually, only this much is the height that is now available. And of course, this length is there. Or the effective area for the water to flow through has actually reduced. Are you able to understand what I'm saying?
Yes, ma'am.
Yeah. Now, bend it further. Bend it further. Now you see that the amount of water that can flow is further reduced because this is actually the effective height that is available and this is the effective area that is available. So now the amount of water that can cut through is smaller. Now, if I hold it like this, and all the water is flowing like this, will any water be able to cut through this area? Are you able to see my hands, guys? Someone please answer. Are you able to see my hands?
Yes, ma'am.
Right. So this is the flow and I have put it flat like this. So the area is actually perpendicular to the velocity. Will any of this water be able to cut through this area?
No.
No. No. So now we come to the conclusion that it is just not the area that is important. It is also the orientation of the area with respect to the velocity field that is important. Okay, you're finding that in the first picture, the effective area that is available for going through is high, but then when you look at the second picture, it is lower, third picture still lower, and in the fourth picture, there is nothing that is cutting through. So now come back to this definition, a measure of flow or penetration of field lines. So volume flow rate is the measure of penetration of field lines through an imaginary fixed surface. So you can just count the number of lines and then say that it is proportional to the flux or the volume flow rate. So now in the first picture you see how many lines are cutting through or penetrating. 1, 2, 3, 4, 5, 6. Now come to the second picture. 1, 2, 3, 4, 5. Less. Now go to the third picture. 1, 2, 3. Only 3 lines are penetrating. Go to the last picture. No line is penetrating this area. Okay? So that means it is just not V and A that are important. It is also the angle that is important. What is the angle that this area vector is going to make with the electric field? That is also important. So in the first picture, what we'll do is we will take this area, draw a normal. This is my n cap vector. I find that my E and n cap are parallel, or theta is 0, where theta is the angle between the V vector and n cap vector. Now look at the second picture. In the second picture, my light blue arrow is my n cap, my dark blue arrow is my V vector. Now look at the angle between them. There is an angle. This angle is theta. Now let us go to the third example. In the third example, theta is still larger. Now come to the last example. In the last example, theta is 90 degrees. 90 degrees. Or n vector is perpendicular to the V vector. Okay, so now mathematically, you can actually put together all these ideas and say that the effective area available for field line penetration is A cos theta. It is A cos theta. Look at the first picture. In the first picture, if theta is 0, cos 0 is 1, so the entire area is available. In the second picture, you see A cos theta. A cos theta is just this. This height plus, of course, the width you have to take. So A cos theta. Now look at the third picture. A cos theta further falls. In the last picture, A cos theta is 0 because cos 90 is 0, or no area is available. Or this A cos theta has a name. A cos theta can be, you're all EG, you're all doing. Some of you have already finished your EG. I'm sure you must have heard the word projection. Have you not heard?
Yes, ma'am.
Yeah. So it is the projection of the area. It's a projection of the area that is actually available. What is the meaning of projection? Let us see. What is the meaning? What did your EG teacher say is projection? What is the meaning of projection? Physically. Okay. If you are not understood, shadow. Very good. Shadow. Like for example, let the area, see, I can't show area, I'm just going to show a line to say this is the area. Okay. So now, if I have a light here, and I place a screen here, that screen will show the entire length of the object. The entire length of the object will be seen there. If on the other hand, I turn it like this, and I have a light here, then what the length of my shadow that I get on the screen is only this much. If I bend it further, it's only this much. If I bend it like this, nothing. Okay, so projection just means shadow. So A cos theta is the projection of the area. Okay, so now we will combine all these ideas and say that volume flow rate is just not the product of V and A. Flux or volume flow rate, flux or volume flow rate is equal to V into the projection of the area or VA cos theta. VA cos theta. Now I want you to recall vector algebra, not vector algebra. You must have been introduced to the concept of cross product in your intermediate days. Do you remember what is physically cross product? Do you remember what is cross product? A cross B is the area of a four-sided figure where one side is A and the other side is B. Do you remember this? Anyone remembers this? Vector. You must recall that if I have a vector A and if I have a vector B forming the two adjacent sides, then the area of this is going to be A cross B. Do you remember this? Nobody remembers this? Did you learn this or not?
Yes, ma'am.
You have studied. Okay. So that means area can be treated as a vector. So from this you know that area can be a vector. Area is a vector. What will be the direction of this area vector? Can you tell me? It's a cross product. So what will be the area? Area direction?
Perpendicular to both A and B.
Very good. It will be perpendicular both to both A and B. If I am talking of A cross B, I put my first right hand on A, then turn it towards B and look at my thumb. Thumb is the normal to the surface and that gives the direction of the area vector. So we are just going to use the same ideas here. We are going to use the same ideas here and we are going to now talk about this area also as a vector. We are going to treat this area as a vector and we are going to write this as V dot A. V dot A. What is V dot A after all? V dot A is VA cos theta. And what is this area vector? Area vector is going to have magnitude and direction. Magnitude will be just the area enclosed by the loop. That will be like, for example, 2 meters square or 5 meters square, whatever. That will be the magnitude. Okay, but what is the direction? Direction is the normal. Same as what you have done in your A cross B, where you treated area as a vector. Same idea you have to take here and treat the normal. That n cap that you have written there is actually the direction of the area vector. Or I can simply write one more equation. I can show what my area vector is. Area vector is modulus of A into n cap, where n cap is the normal, unit normal drawn to the area. Did you understand whatever I discussed on this page, guys? Well, Pondra, I will stop teaching if you people behave like this. Answer.
Yes, ma'am.
Then is it so? I don't know. What should I give you for you to say yes or no? I'm not always expecting yes. You can say no. If you're not able to understand something, say no. That would be actually better than the silence. At least I can repeat. I can maybe present it in a different fashion. Is there somebody in the class who can actually explain what I just talked about flux? The page is there before you. Please do that. Name it. Tell your name and do it, please. You can be wrong. Absolutely no problem. Please do it. In live class, we face a problem where students keep on talking. And here, we are facing a problem where students are refusing to talk. Someone who can talk? Well, then I will only think that you're all Buddhas, you understood everything, you cannot spend time talking to ordinary people like me. Okay. So flux can be regarded as, I just explained some time back, you can numerically or pictorially look at flux. This concept of flux can be pictorially represented as the number of field lines cutting through a loop area perpendicular to the stream, through a loop area perpendicular to the stream. So look in the first picture, the entire area is perpendicular to the stream. So you can see how many lines cut through. Now go to the next picture, you have bend the area. Now if you see what is the effective area available, this is the effective area available. There's nothing different from what I showed in the previous slide. In the previous slide, it was a two-dimensional picture. Here it is three-dimensional. That's all. Okay, the area is shown. You can see effectively how the area has become small. Okay, and you see the number of lines cutting through 1, 2, 3, 4, 5. Now go to the next picture. The next picture, you are putting it this way. So nothing is actually cutting through. The flux is 0. Flux is 0 here. Flux here is equal to V into A. In this case, it is VA cos theta. Okay, so in all these cases, what is common is you can simply combine all these three things and then write flux in general can be written as V dot A, which is VA cos theta. And what is theta? Anyone? What is theta? Look at this picture and tell me what is theta.
Angle of rotation.
Angle between the velocity vector and the area vector. Velocity vector and the area vector. Okay. And I have been talking about surfaces which are not three-dimensional. I'm not talking of surfaces which are three-dimensional. I'm talking of flat surfaces which I put in the path of the flow. Okay, now you can also similarly talk about closed surfaces, closed three-dimensional surfaces. When I say closed three-dimensional surfaces, it is not solid closed. That's not what we mean by closed. When we are saying closed surface, what we mean is three-dimensional, but through which water can flow. Like for example, I'll give you an example. If I take a wire, okay, I take some wires and then connect them in this way so that I'm able to get a cube like this. This is an example of a closed surface. This is an example of a closed surface in the sense no edge of the surface is open. Everything meets and forms a closed surface. But then it is going to allow the fluid to flow. It will allow the fluid to flow. In that sense, it is open. But then when we say closed surface here, we are not talking of cardboards kept like this and then closed so that nothing will enter or go. No, that's not what we mean. Here, when we say closed surface, we are talking about a surface where there is no open edge. No open edge is there. This entire thing has come together, but fluid can still flow. So let us look at what is the net flux through a closed surface. If I want the net flux through a closed surface, let us say how many sides will be there for a cube? For a cube, how many sides will be there?
6.
6 sides are there. So what we have to do is we can get the flux for side 1, side 2, side 3, side 4, side 5, side 6. Okay, for each of these faces you can get and then add everything. Add everything. That will give you the net flux through a closed surface. For a closed surface, you have to get flux like this. Okay, whereas if it's just one surface like this, then it is through that surface. But if I am talking about a closed, like for example, you look at this. This picture is showing you a closed surface. So it has got how many sides? 2 triangles. Then this side there is a square. This side there is a rectangle. So it is 5-sided. So there are 5 vectors: A1, A2, A3, A4, A5. So you have to find out the flux through each of these and then add them up. Okay, that's how you get the flux for a closed surface. And when you're talking of closed surface, one very important thing that you should remember for a closed surface is that when you are talking of area vector for a closed surface, you have to consider the outer normal to the closed surface, an outward normal. You have to consider the outward normal. Like for example, I have my remote here. This remote is a closed surface. It encloses a volume. If I am talking about what is the A vector for this top surface, the A vector will be an outward normal. Similarly, for this lower surface, it will be an outward normal. For this surface, this. For this surface, this. For this, it is this. For this, it is this. Always take the normal, which is outward to the closed surface. So this is the major deviation from simply a flat surface that we have taken as the first example. Okay, so for a closed surface, what should you do? Individually, for each of these faces, you have to find out V dot A1 plus V dot A2, V dot A3, like this do for everything. And it can be shown that for this kind of a closed surface, it can be shown that the flux will be equal to 0. It can be shown that the flux is equal to 0. Okay, I will not do any mathematics to show that. Just pictorially I'll show you. You see here, if you look at this surface, this A1 surface, and see the number of lines which are entering 1, 2, 3, 4, 5. And if you see the number of lines cutting from the other side, you will again find 5. And what did I say is pictorially flux? Flux can be pictorially represented as number of field lines cutting. So you can see 5 field lines are cutting here, 5 field lines are cutting there also. There, and then through the other 3 surfaces, nothing will cut because they are actually, the normals are perpendicular to the velocity vector. So it's only through this surface and this surface that it is cutting. And you're finding that same number of field lines are cutting. So we can show that the flux is 0. You can actually show that for this surface, the flux is going to be minus VA1, and for this surface, you can show it is VA3 cos theta. And here it is negative because V and A1 are anti-parallel to each other. My V vector is going to be like this, my A vector is opposite direction, so this angle is 180 degrees, therefore minus VA1. Whereas in this case, it is going to be plus, but then my area vector and my velocity vector are making an angle theta. We can show that one is negative and the other is positive, and we can show that they are going to be equal and opposite, and the sum is 0. Instead of doing it mathematically, I just use the number of field lines entering and going out, and thereby telling that if 5 lines are entering the volume, 5 lines are also coming out. Therefore, in one case the flux is positive, negative, the other case it is positive, and it is equal and opposite, therefore 0. Okay, and another thing, I already used the word negative, positive. Flux can be negative, flux can be positive. Flux is positive when field lines emerge from a closed surface. If field lines are going to come out like this, field lines are coming out. Now you're finding that the area vector is also an outward normal. Okay, you're finding that theta equal to 0 in this case. Therefore, flux has to be positive. Okay, or let me even take a surface like this. Here also, the area is this, and then my velocity is this, theta is this. So whenever my theta is going to be less than 90, 0 to 90, then flux will be positive. And in all such cases, field lines will be coming out of the closed surface. So here is my closed surface and field line will be emerging. It will be coming out. Okay. Now, on the other hand, let us look at another situation. Field line is entering the closed surface. Sorry. Field line is entering the closed surface. Okay. And what is my area vector? What will be my area vector here for the surface? It will be
It
outward.
would be anti-parallel.
Anti-parallel. Anti-parallel. Therefore, theta is 180 degrees and you know cos of 180 is negative. Therefore, negative. Or let us even take a surface, okay. I mean, like this, you can take any number of examples where, let me take another example. So let's say this is my surface. My area vector is going to be in this direction. My velocity vector is going to be in this direction. I find my theta is greater than 90. My theta is greater than 90. In this case also, I'm finding that the field line is entering into the surface. Okay, so I'll just rub this part so that there is clarity. I'll sum up everything that I have just said till now and say that whenever field lines emerge out of a closed surface, whenever field lines emerge out of a closed surface, then theta will be lying between 0 to 90 degrees and flux will be positive. On the other hand, whenever field lines are entering into a closed surface, then theta will be going between 90 to 180 degrees, greater than 90 to 180 degrees. In these cases, what happens is flux will be negative. Okay? So, and I hope you understood the concept of positive and negative flux. Okay? Just take any surface. If a field line is entering into the surface, you know that the area vector and the field lines are making an angle more than 90 degrees, therefore negative. If the field line is coming out of the closed surface, field line and area vector will be making an angle less than 90 degrees, therefore positive. So you can just generalize and say that for any closed surface, if field line is entering, for that surface the flux will be negative. If the surface from which it is coming out, for that the flux will be positive. Clear, guys?
Yes, ma'am.
Yeah. So now what we have taken the example of velocity flow, at least that you can visualize, you can think of water flowing. That's why we took the example of velocity flow. Now, think of a situation, we talked about uniform flow. Uniform flow means what? If I have an area, if I'm having a surface, then at all points on the surface, the velocity that is hitting is going to have the same value. That is uniform. Okay, but then that need not always be the case. That need not always be the case. There may be a situation where it is not a uniform flow. Let us say we are talking about a flow through some pipe which is not having a uniform cross section. So let's say it is a pipe that is increasing diameter. Okay, then what will happen? The velocity flow may be like this. The velocity field may be like this. Okay, and it may have different values also. So you're talking about a non-uniform velocity field. And you may also have a situation where the surface, the closed surface that you are talking about is not a beautiful cuboid or a cube. It may be some randomly shaped object. It may be some randomly shaped three-dimensional structure through which it can flow. Okay, so under such circumstances, what you have to do is you cannot take an entire surface and say this is my area, everywhere velocity is the same, so V dot A. No, you cannot do that. So under such situations, what you have to do is you have to go to calculus. You have to use the method of calculus. You have to divide the area into number of small elements. You have to divide the area into number of so small elements, so small that each of this element has an area dA. Each of them has an area dA, and it will be so small that for that area, velocity is a constant. For that area, all over that area, velocity is a constant. So the flux for that small bit will be d phi equal to velocity dot dA. Okay. Now I want the flux for the entire closed surface. So what should I do? I have to do integration. So when I do integration, it will be flux is equal to integral d phi. Okay, so that becomes v dot dA. So what is done here? Here you are using the method of integration. V is the, and what is V? Remember, V is not a constant anymore. For this particular area, that this particular dA, for this dA, the velocity is some V. For this element, it may be something else. For this element, it may be something else. Okay, so and now do an integration V dot dA. And this is going to be, look at, notice this is a surface integration. Have you heard of surface integration, guys, in mathematics? Okay, this is called surface integration, and this circle here means it is over a closed surface. For the closed surface, you're doing the integration. So this is called a surface integration over a closed surface. And what is dA? dA is the infinitesimally small area element that you have taken. So small that for that area, we will have the same value everywhere on that area. Okay. So this is a more generalized definition of flux. We started off with, first our definition was V dot A. This was for a surface that was plane and V was the same everywhere. Then after that, for a closed surface, we said flux is equal to summation V dot A. Now we have gone to an irregular shaped surface, closed surface, and the field is also not uniform. Then it has to become more general, and it will become flux is equal to integral V dot D. Are you understanding? From the most simple, we are proceeding towards a complex situation. Okay. Next, let us look at three final results that I want to show you today. So flux is equal to integral V dot dA for the closed surface, and flux will be zero. Please remember, these are golden rules that you have to remember. Flux is zero if the surface encloses no sink or source. Like for example, let us say this is my closed three-dimensional surface and there is no sink or source. I hope you have heard of sink and source in the context of thermodynamics and in the context of heat and all that. Yes or no?
No, ma'am.
Yeah. This semester you have thermodynamics, no?
Yeah, but we haven't came across the terms yet.
Okay. Carnot's engine and all have you studied in your intermediate?
Yeah, but I don't remember it.
Okay, I will just tell you something. Have you people gone to some place where you see some water springs? You can't see the source, but then water keeps on coming continuously. Have you seen that when you went on some tour?
Yes, ma'am.
Yes,
You must
ma'am.
have seen. Okay, that is a sink. Similarly, sometimes what happens is in the ground there will be some place which will keep drinking the water. You won't be able to see that place, but it gulps all the water. That's a source. I'm sorry, that is called a sink. And source is the water keeps on coming. That is a source. So the source is going on giving out the water, and sink is something that is actually taking in the water. In nature also you have such source and sink for water. So we will take the example of water flow only. Okay, now let us say I am putting this wire mesh, a closed surface, in the path of water, and let us say the water is flowing, entering from one side and going out from the other side. There is no sink or source inside. Then what happens is you can see the number of lines entering will be equal to the number of lines which are emerging, or flux here is positive, negative, and flux here is going to be positive. So net flux will be zero. Is that difficult to understand?
No,
Yes,
ma'am.
ma'am.
This you understood. Okay. Now I will talk about another situation. Okay. Let us talk about this kind of, again, a surface, a three-dimensional surface, which you're putting in the path of fluid. And let us say that there is a source here. There is a source here which is going to give out water. A source that is going to give out water. And you're placing this entire contraption in the path of some other flow. Some other flow. Then, if you see what is the volume of water that is entering per second, volume of water entering per second, that is the inward flux. The inward flux. Okay? And if you measure at the same time the outward flux, the volume of water per second flowing out, which will be greater? Will they be the same?
No, ma'am.
Why will they not be the same?
Because the object is also
Having
the
a
object is a source.
there is a source. So that is also giving out water. So certain amount of water that is also giving out. And your container can hold only so much. So what will happen? The water that is entering per second will be less. The water that is going out will be more per second. And out is always positive. Yes or no? Out is positive. That's what you're seeing for flux. And going inside is negative. So if you compare here, you're seeing that the flux of the outward flow is going to be greater than the flux of the inward flow. Okay. So what will be the resultant? What will be the resultant? The net flux will be positive or negative?
Positive.
Positive. Therefore, the flux for a closed surface will be positive if the surface encloses a source, and flux will be proportional to the source strength. It will be proportional to the source strength. Otherwise, what happens? You have the surface, this closed surface, water is flowing in per second, 10 liters flowing in per second, 10 liters flowing out per second. So what is that extra that is coming? That extra is coming because of that source inside. If the source is going to give out 1 liter per second, so the net will be 1 liter per second. Following that? So it depends on the source strength. The net flux will be proportional to the source strength. Instead, if my strength, the source is going to give out 5 liter per second, then what will be the net flux? The net flux will be 5 liter per second. So you can say that the net flux will be positive and it is going to depend on the source strength. It will be proportional to the source strength. Now let us look at another example. Let us see what happens if I am having a closed surface like this. Okay, fluid is going to enter and fluid is going to come out. But then let us say there is some kind of a sponge here, some kind of a sponge that is capable of gulping water. Gulping water. Then what does the sponge become? Sponge is a sink. Sponge becomes a sink. So let us say that there is a flux, inward flux phi in, and there is an outward flux phi out. Which will be greater? Will all the water that entered go out? Some part of that water is going to be swallowed by my sink. So what happens in this case? Inward flow will be greater. Outward flow will be lesser. Inward flow is always negative. Therefore, when the inward is going to dominate, then my net flux will be negative. Negative. And in this case, what happens? There is a sink inside. And how much will be the net flux is proportional to the source strength. Sorry, I should not say source strength. What should I write there?
Sink.
Sink strength. I should write sink strength. Okay, so I hope these ideas they have discussed deliberately using this water and all that, so that you understand that concept of a flux. What is flux? Flux is volume flow rate. That is volume flowing per second through an area held perpendicular to the flow. Okay, next we talked about a closed surface. In a closed surface, we have to always take the area vector as an outward normal at every point. Now, if my velocity is not having the same value everywhere on the area and my surface is not having a regular shape, then my flux will be integral V dot dA. Next, we have seen what happens if my surface, my closed surface does not have any sink or source. If it doesn't have any sink or source, the volume flow rate entering will be the volume flow rate going out. Therefore, the flux will be zero. Then next we saw that if we have a source inside, then more goes out than enters. Therefore, the flux will be positive. Then what happens if there is a sink inside? If sink is there, it gobbles up all the thing coming in. Therefore, outward flow will be less than the inward flow. Therefore, the flux will be negative. You understood all these guys?
Yes, ma'am.
Right. So now, the next class, what we'll do is all these ideas. See, the water flow and all that, it is not difficult for you to visualize, right? But all these ideas we will in the next class translate to electric field. That's all. And it will be easy, don't believe me, it will be easy if you have understood today's class properly. Any doubts?
No, ma'am.
Okay, then I will stop. Okay, so I think you're going to get a weekend, right? A weekend followed by some break also. Okay, have a nice time. That's all I will say. Good day then. Anything you want to say? Okay, there's nothing. Let me stop.
Thank you, ma'am.
Yeah.
Thank you, ma'am.